I am having some Wi-Fi issues here, so I'm not exactly sure if the recording has started, so I will assume that it has started. As we said, density of seawater is dependent on temperature, salinity, and pressure, but for most practical purposes, ocean water is still incompressible. So we wrote before density of water as a reference density plus sigma, and we had written sigma as a function of temperature for doing many of our large-scale balances like thermal winds to show horizontal temperature gradients driving vertical geostrophic shear. Right? Getting back to that, we write sigma as rho minus rho f, and the thermal expansion coefficient at constant pressure and salinity is minus 1 over rho ref d rho dt. Obviously, as temperature increases, density decreases, so you get a minus sign here, and we'll see that the alpha t is actually quite dependent on pressure, and it's not constant, also varies a lot with temperature. Similarly, you have a density dependence on salinity, so that's the beta S salinity coefficient for density, 1 over rho ref d rho ds, where you hold temperature and pressure constant in this case. So density of water then can be written as sigma equals sigma naught plus rho ref times minus alpha t minus t0, again to make sure that we get decreasing density with increasing temperature, plus beta s minus s0. We will see that depending on where you are, the impact of temperature is typically much higher than salinity, but it depends on whether you're in the cold temperature range or the warm temperature range in terms of the density change you will get for similar amount of temperature change, for example. Okay, what does that mean? Essentially, even though this equation looks very linear, the density dependence is actually quite non-linear, which makes for some very interesting properties of ocean water. So talking about properties, these are physical properties of liquid water. Specific heat, 4.18 10 to the 3 joules per kilogram per Kelvin. This is much higher than air, of course. Latent heat of fusion, latent heat of evaporation, which is important because that's the energy exchange between the ocean and the atmosphere. A lot of it has happened. A lot of the energy exchange happens through evaporation, where the hydrogen bonds between the water molecules is broken and the molecules are grabbed from the ocean, put into the atmosphere. So the ocean loses energy and cools down, and the atmosphere takes the water vapor, and when it condenses, obviously the atmosphere heats up, which is what drives convection and the circulation. But also in the ocean, because you have salt, when evaporation happens, salts are left behind. So there are regions where evaporation can leave behind so much salt that the density becomes very heavy and the water can sink. Water parcels begin to sink. That's the ocean version of convection. Okay. Density of fresh water maximizes at 4 degrees centigrade, as you know, 0.999 times 10 to the 3. As you go below 4 degrees, water begins to expand and density actually drops off. That's in kilogram per meter cube. Viscosity, kinematic viscosity, and thermal diffusivity. Turns out that thermal diffusivity and salt diffusivity are also different by 2 orders of magnitude, which means the heating and cooling of the surface can penetrate much more quickly below the surface, whereas changes in salinity don't diffuse so fast. Thermal diffusivity is not so important in the ocean anyways, but nonetheless. Let's look at the values of alpha t and beta s at the surface and at a depth of 1 kilometer here. and at various temperatures going from minus 1.5. Why can we go to minus 1.5? Because when you add salt, water's freezing temperature is lowered. So instead of freezing at 0, it can go down to minus 2 depending on how much salt there is, right? So at 5 degrees and 15 degrees, and at depth you have minus 1.5 to 3 degrees and 13 degrees. And the main thing to notice is that alpha T, which is missing here, is non-linear with temperature change. It goes from 0.3 to 1 to 2, and it has a pressure effect. So you can see that it's 0.65 at the same temperature when you go to depth of 1 kilometer because of pressure, and it increases to 1.1 and 2.2 as temperatures warm up. Okay, whereas salinity change is not that large as temperature range. Okay, and the salinity expansion coefficient is also fairly constant. So the density then varies. You can see that the density increases and then decreases as you get warmer. Okay, so this is sigma here, so it is, you have to be careful. It's 1028 minus 1000, so sigma is 28, 29, 28 as we talk about. Now there is beta S at the at depth, which has more variation because of the pressure effects, and there is the sigma that is at depth. Okay, so water has quite a different behavior than the atmosphere. In the atmosphere, pressure drops off exponentially with height, whereas in the ocean it doesn't increase exponentially with depth. The most interesting thing then of the density dependence on salinity and temperature in the real world, because of these nonlinear expansion coefficients and salinity dependence, you get these non-linear density changes. So these are constant density sigma surfaces. Okay, again, this is deviation from reference density, and if you zoom in here, you can see that the slopes are different. So as you go to warmer temperatures, the slopes are steeper here, for example. Okay, so temperature dependence gets larger. But you can see something else here. You can take a water parcel that's here and here. They're on the same sigma line, but they have different salinity and temperature combinations. Here it is 33.9 and then let's say 5 degrees centigrade, and here it would be 36.5 and let's say 20 degrees centigrade. So you can take two water masses with the same sigma, mix them up, the salinity will be averaged, the temperature will be averaged, so you end up on a different sigma surface. So you can mix two water masses with the same density and produce a third density, a second density. Why? Because of this non-linearity. That process is called cabling, C-A-B-B-L-I-N-G. That's something very special about water because of the non-linearity of water's density, because of temperature and salinity dependence being a polynomial of fifth order. Okay, that's where the non-linearities come from.